welcome back. So let me remind what we proved in the last class. We proved a bound on the entropy. So we showed that the entropy at time t, it's bounded by the entropy at time 0 minus the Dirichlet form, which I will put on the left-hand side. So let me write that more as there is a constant here, might be 2. So this is what we proved in the yesterday. And I want to use that bound in order to close the equation in terms of the martingale. So if you remember, we consider a function g, which is, say, of class C2, and a martingale associated to this test function, which was the empirical measure which is integrating minus the empirical measure at time 0, and then minus Ln, the generator of the exclusion process. And we have seen that we want to look at this process in the time scale n square. And here, so I have n square. I'll change variables here, saying that S prime it's equal to S divided by n square. So to move, so when S it's equal to t n square, this becomes t. And ds prime will make n square Ln to appear. Now we computed this expression, and we obtained that this is equal to sum so there were many terms, but say that all terms looked like had this form. So either eta x plus e, or eta x plus 2e, but they were all products. Okay, there were one which was simply eta x. This one was not a problem, but the terms making trouble had all these form, because I couldn't write this sum as a function of the empirical measure. Okay? So all my problem is to take an expression like this. So mind that I have the empirical measure at time S n square. And here I have a function which is continuous. And I would like to say that, well, this expression, it's close to an expression which is a function of the empirical measure. Okay, say something like that. Because if I could do that, then I would have expressed the martingale in terms of the empirical measure, and then I could pass to the limits, saying that, well, if Pn it's a sequence which converge to P, then if this martingale it's small, the limiting measure will be concentrated on configurations on trajectories pi such that pi t g minus pi minus this integral of f of pi is small, okay, or 0. So we need to replace this expression by a function of the empirical measure. So this is the goal of the day. This is what we want to do. And which function? So let me argue. So here is the space, 0, 1, our torus. And here we have an average over this torus. Okay? So my claim was that if we observe the system in a small neighborhood, due to the interaction of the particles, what I observe immediately is that locally there is a local equilibrium which appears. Okay, so the idea is that if you look at a small neighborhood, you have all these particles. These particles are interacting among themselves. And so the boundary effects are not very important. So you can imagine that in small intervals of time, there are many particles entering the system or leaving the system, so that essentially you have a closed system. And due to the interaction of the particles, this closed system will, because you're looking at a very small neighborhood, this closed system will immediately be very close to a stationary state. But the stationary state may be different from one neighborhood to the other neighborhood. And so, if at some time t, I observe the system around a point x, what I expect is that locally, what I will observe is a state which is very close to a stationary state. And I know what are the stationary states. The stationary states are the Bernoulli measures with some density alpha. So what I expect is that very close to this point, what the state will be very close to a stationary state, a Bernoulli measure, with some density, rho tx, which I do not know what it is. But I know that what I expect is that the distribution of particles in this small neighborhood will be very close to the distribution I observe if the measure is a Bernoulli measure with density, some density, rho tx. And if this is the case, and I look at this sum, so at time, so say Tn squared, eta x plus e time Tn squared, g second of x. Well, this means that here there is some sort of averaging in space, because I can claim that g of x, since this function is continuous, it's very close to an average of this function on a box of size L over n. Okay? So I'm taking here a box of size L. So this, in my scale, will be L over n. So L, it's large, but it's fixed. So what I'm claiming is that this is very small, right? Because g second, the second derivative, is continuous. So if I compare g at this point x with g at the point y, where I'm doing here the average over L sides. So this cube has L sides. Okay, so these points y are equal to y plus k over n, for k smaller than L, y it's equal to k plus x, k over n, where k is bounded by L, right? So I'm doing a sum here over these points. And I'm saying, well, the distance between y and x, it's bounded by L over n. L, it's fixed, and it's going to infinity, so this is very small because g is continuous, okay? So this is small, which means that I can replace g of x by this average, right? Now, once I replace g of x by this average, so I just have this expression. And now let me integrate by parts to say that, so this is very close to 1 over n. So I will sum first over x and then over y. So this is a sum over y of g second of y. And here I have 1 over 2l plus 1, a sum for y minus x bounded by L over n of eta x Tn squared, eta x plus e Tn squared. So I can introduce in my system this average. Okay? So an average in this small neighborhood. So you have to understand that this neighborhood, it's very small in the macroscopic scale, because L over n is small, but it's very large in the microscopic because I'm summing over L terms. There are L points, okay? And L is very, very large. Now I say, well, if it's true that the state is very close to this one, then by the law of large number, this average should be close to the mean. And the mean would be, well, the mean with respect to the Bernoulli measure of the function which I'm averaging. So there are two approximations. First, I'm saying, well, the state, it's very close to this one, so I'm replacing the state by this state. And then there is the law of large numbers, which is telling me that this spatial average should be close to the expectation, which is the law of large number. And well, this expectation, I'm very happy because this one I can compute. It's rho tx squared, because these variables are independent and they have expectation rho tx. So what this is telling me is that, well, eta x Tn squared times eta x plus e Tn squared should be close to rho tx squared. The problem is that I don't know what rho tx is. I still don't know, right? I'm hoping to find it as a solution of a PDE. So what I will do is, well, I will replace this rho tx by the empirical average, which means that I will consider this small neighborhood, and I will compute what is the density of particles over there. So the density of particles, I will represent it by L, eta L at x. So x, it's here. So this is the average of particles on a cube of size L around x. So this is 1 over 2L plus 1, y minus x less or equal than L over n of eta y. Okay, and that, so I will say that this is close to eta L at x at time Tn square. Well, to replace this special average by its expectation.
But so you have to put L as a growing function in terms of x?
Yeah, so let's say that I'm taking first a limit in n and then a limit in L. So L, indeed, in order to replace, I need L to infinity, to send L to infinity. I need a very, very large. So I could take here any L growing to infinity together with n, for instance. N to some power. All right? So this is telling me that, well, let's try to replace this product by this square. The problem, however, is that this is still not a function of the empirical measure. Okay? Because, well, L is fixed. I'm taking the average over L sides. This is not a function of the empirical measure. However, if I take L of size epsilon n, then this is 1 over 2 epsilon n plus 1, the sum of y minus x bounded by epsilon of eta y. And now this is a function of the empirical measure because this is n, if you wish, 2 epsilon n plus 1, 1 over n. And here I'm taking a sum over y of a function which is the indicator of x minus epsilon and x plus epsilon of y eta y. So this is, well, something which will converge to a constant. And here's the empirical measure of pi n with respect to this indicator function. Okay. So if I'm able to replace eta x plus e by eta x epsilon n to the square, so this empirical average of particles to the square, I'm in business. Because this one, it's a function of the empirical measure. Okay, so my goal will be, so this is all heuristics to tell you that what I want to prove is the following statement. That this is small. I will try to prove that this is small. So this is my candidate, and so I try to explain why I want to compare this function with this one. But what I'm also saying is that, well, this last function, it's a function of the empirical measure. Okay, so two claims. Do you agree that this average is a function of the empirical measure? So that's the first question. And then, well, okay, then there is the heuristics that either you buy or you don't. This is hand-waving, but I'm really I hope that I convince you that, okay, why we expect this function to be close to that, because actually there is a space average, which I can insert here, and So I'm not comparing this one with this one, but the average of this one with respect to that one. And then I'm comparing two types of average. All right? So questions. So now maybe it's time for questions about these heuristics. Otherwise, I'll just prove. I'll state the theorem and prove it. So any question? And this is, I mean, the central point. So this is called the entropy method, the GPV method, because it was first proved by Gould, Papanikolaou, and Varden, and it's at the earth of the theory of hydrodynamic equations, or hydrodynamic limits. Okay? So if you have no question, let me write down here the theorem. So I'm starting with a measure, an initial measure, and I have here a function, maybe let me call it f, with, in our case, will be g double prime. I just want it to be continuous. Sorry, this is not x over n, it's x. Yeah, wherever I'm writing x over n, it's actually x. And then I'm taking v of epsilon n of eta s n squared, the s. I'll take the absolute value. And I want to take the limit as n goes to infinity of this expression. And what is v? Vx. So this is the function v at x. Depends on epsilon and on n and on the point at which I'm computing. Okay. So mind that the same argument will say that if I have here a product of 3 terms, then this argument will say, well, I have just to take 3 terms. I will get a cube, so I'll be comparing with a cube. Okay? So any finite product, I'll be just replacing here 2 by the number of terms. And what I will need is actually to prove I'll have to send epsilon to 0. Okay, so this is the theorem I will. Okay, fine. So, and I will be using this. So remember that h nt is the entropy of, I start from an initial measure, then I let the process evolve, but here I'm looking at times of order Tn square, and I'm comparing that with respect to a stationary measure, nu alpha. So let me see what is the order. Okay. And here I have a bound Hn0, so let's see what's Hn0. So Hn0 is this relative entropy, and I want to compute it. Okay. So let's compute to see what is the order of this entropy. Okay, so I take a measure, mu, and I compute its relative entropy with respect to nu alpha. All right, so this is the entropy of mu n with respect to nu n alpha. And so let's recall the formula. The formula is that d mu n, this is the mu. Okay. So this measure, it's the stationary measure, so it puts positive weight to any configuration. So any measure, it's absolutely continuous with respect to this one. And therefore, the entropy, the relative entropy, it's given by this formula. Okay, so this is equal to the expectation. So I can cancel these, and actually this is an expectation with respect to d mu n of this log. Fine? Okay, so I'll compute and I will bound it. So I'll compute this entropy with, if mu n, it's a product measure with a certain profile. So I fix a density profile, rho, and now I compute this relative entropy, taking mu n to be that. Okay, so remember that here, nu rho at a configuration eta, it's equal to the product x in lambda n. And then if I have a particle at x, the probability of having a particle is rho x, and the probability of having a hole, it's 1 minus rho x. So this is the expression of nu rho. Okay. It's the product at each site. At a site, if I have a particle, the probability of having a particle is rho x. So if I have eta x, it's 1. This will give me a contribution of rho x, and this a contribution of 1. So indeed, it's rho x. And in the other way around, if there's a hole, it's empty. This is 0, so that's 1. And this is 1, so that's 1 minus rho x. Okay, so this is the formula. And then I will just plug this formula in this equation. Okay. And I have the same formula for nu alpha. And nu alpha, it will be the same thing, but with alpha instead of rho. So this means that the entropy of nu n rho with respect to nu n alpha, that this is the log. And now let me just replace. So actually I have a product x in lambda n. And on the numerator I have just this expression. So this is rho x eta x, 1 minus rho x, 1 minus eta x. and this is divided by alpha eta x, 1 minus alpha, 1 minus eta x, and this is with respect to mu n, and mu n, it's nu n rho. Okay, so, well, I have a product with a log, becomes a sum. And then, well, I have all these terms, so I have eta x, which is taking the log of rho x alpha, then plus 1 minus eta x log of 1 minus rho x, 1 minus alpha, d nu n rho. Okay? But, so what is the expectation of eta x with respect to this product measure? It's rho x. And the expectation of 1 minus eta x, it's 1 minus rho x. So this is the sum of rho x log rho x divided by alpha plus 1 minus rho x log of 1 minus rho x, 1 minus alpha. Okay? And, well, this computation works in any dimension. So let's say that we are in dimension d, so just to fix ideas. So this means that if I divide this entropy by d, n to the power d, that will converge. Well, this is a Riemannian sum. Let's say that rho is continuous. So that will converge to the integral over the torus in dimension d of rho log rho divided by alpha plus 1 minus rho log 1 minus rho divided by 1 minus alpha dx. Okay? So this tells me that the entropy is of the order n to the power d. Okay? Because if I divide it, I get a finite limit. And this gives me the asymptotic entropy of a density profile. Okay? So this is computation, and this tells me what is the order of the entropy. This is the asymptotic limit, right? So this is the exact order of this entropy. So now what I claim is that, well, this is actually bounded by constant times n. And I can't get anything better than that because, I know that for some measures, this is exactly of the order n in dimension 1. So I can't expect anything better than that. And what I will prove is whatever the measure, I get this bound. And n to the power d if I'm in dimension d. Right, so why is that? So let me go back to this computation. And my claim here is that mu of eta it's a configuration, mu it's a probability measure, so this is bounded by 1. Okay? So this is bounded by log of 1 over nu alpha of eta d mu. And, well, I just computed here what's nu alpha. So the log of 1 over nu alpha eta, it's equal to the log minus, so I have here the product of alpha eta x, 1 minus alpha, 1 minus eta x. And so this is minus the sum of eta x log alpha plus 1 minus eta x log 1 minus alpha. And alpha is something between 0 and 1. Okay, so maybe let me put that back here. So this is positive. This is larger than 1. So log it's positive. Eta x is bounded by 1. The same thing here. 1 minus eta x is bounded by 1. So this is less or equal. I have here n to the power d terms. And so this is bounded by log of 1 over alpha 1 minus alpha. Okay? So, and this is uniform over all eta. Okay? So I have this bound. And therefore, this is bounded by constant to the power nd, where the constant is that function of alpha. So this is of the order constant times n, because we are in dimension 1. Okay. So that gives me the order of the entropy. So let me start to estimate So let's see what I can do. Let me call whatever appears here as a function h of s, h of eta s ds. So this is the expectation of mu. So I'm starting from a configuration eta with a certain probability, mu of eta. And then I'm taking this expectation. Okay. Now this is a function of eta. Let me call that r of eta. Now I want to use the entropy inequality, which we proved, to say that, so this is the expectation of r with respect to mu. So I'll say that this is bounded by the relative entropy of mu n with respect to the stationary state nu n alpha, divided, I know that this is of the order n, so I'll divide that by gamma times n to have something now which is of the order 1 divided by gamma. I'll send gamma to infinity, so that will be small. Plus 1 over gamma times n And then here I have the log of the expectation with respect to nu alpha of the expectation of R times gamma times n. Okay? So this is the relative entropy, the entropy inequality. Fine. So I'll forget about the first term. I'll concentrate on the second one. Because I know that the first one, it's bounded by 1 over gamma. Okay, so this one, it's bounded by 1 over gamma. So at the end, I will have to send gamma to infinity. So let's look at the second one. The second one is 1 over gamma and log of the expectation with respect to nu alpha. So now I'm happy because I have nu alpha. And then I have the exponential. So maybe let me write it. Okay, this is the second term. The expectation with respect to log of the expectation with respect to nu alpha of the exponential. And there is gamma n, which I forgot. Okay, it's the exponential of gamma n times r. Gamma n, I can put it inside the expectation. Now I can say, I can use Jensen equality to plug the exponential inside the expectation. Okay, the exponential of the expectation, it's bounded by the expectation of the exponential. Right? And this is what we write as, well, we are starting from the stationary state. Right? Now I want to say that what bothers me is this absolute value. Everything I'm doing here is just to take care of the absolute value, which I don't like. So now I'm saying that, well, the expectation of the absolute value so this expression, it's bounded by the expectation of gamma n 0t h eta s ds plus the expectation of minus gamma n 0t h eta s ds. Okay? The expectation of some number, it's always bounded by the expectation of this number and plus the expectation of minus this number. And therefore, I have the 1 over n log of this sum. Okay, but so I don't want this plus, so I'll say that the log of the sum. So let me call an the first term and bn the second term. So this is an and this is bn. This is less or equal than the log of 2 times the maximum between an and bn. And remember that I have 1 over gamma n. So this is equal to 1 over gamma n. So the log of these two, this is log of 2, plus 1 over gamma n, the log of the max. So this one tends to 0 because n will go to infinity. So this one I don't care. And this one, it's bounded by 1 over gamma n log of an plus 1 over gamma n. So log of the max, it's equal to the max of the log. And the max of the log, it's bounded by or if you wish, the max of these two terms. So what I need to show is that each of these two terms converge to 0. And these terms are exactly this one, but without the absolute value. Either I take h or minus h. So h or minus h means here in my functions that I will take either f or minus f. But the sign of f will not matter. So after these arguments, I'm left to show. So in conclusion, the conclusion is that what I need to estimate, it's 1 over gamma n, the log of the expectation with respect to the stationary state of the exponential of gamma n 0t hs ds with a plus or minus in front. Okay? So this is what I need to estimate. So I need to take the limit as n goes to infinity and then as gamma goes to infinity. Because I need to send gamma to infinity. Okay? But now, mind, I don't have anymore the absolute value. All this argument has been cooked up just to remove this absolute value. And the problem is there are two differences. Well, fine, I don't have the absolute value. Fine, I don't have this initial measure. Now it's the stationary measure. However, the problem is that now I have an exponential inside the expectation and the log. So this was the price to pay in order to remove that absolute value and to replace the stationary state, the initial measure by the stationary state. Okay? So this is what I need to estimate. So I need to estimate the exponential of a function h of eta s. Or maybe let me call that r again. So r will be, so I obtained a gamma n, so there is a gamma n here in front. And 1 over gamma n and a log. So just remember that I'm okay. So just keep in mind that what we need to estimate is this. And since there is this formula, let me consider this expression. And then I go back. So I'll get a formula for that, and I return to this expression later. Okay, so what I want to define it's a new semigroup, which I will represent by PRT. So R is that function which appears in this exponential. And PRTF will be, you take the expectation of eta, and you compute the exponential of 0t r eta s ds, f of eta t. So let me define this operator. This operator acts in a function over a function f by this equation. And what I claim is that this is a semigroup, and this semigroup, if you take its derivative, it is given by L, the semigroup of the Markov chain eta, plus R. Okay? So what I claim is that we have this equation. So that this defines a semigroup, and the generator associated to the semigroup is given by L plus R. So let's assume that, and at the end, I will prove this equation. Questions? So what I want to estimate is this expression. Okay? So this expression, I can write it as a sum over eta of nu alpha eta of the expectation starting from eta of the exponential integral from 0 to t r eta s ds. Questions? Okay. So let's go back to what we want. We want to estimate this expectation, which is equal to that one. Fine. So now by what we wrote here, this is PTR computed at the function 1 at eta. Right? I can just add here, think that f is equal to 1, and therefore this is PTR1. And so what I get is that actually this is equal to PTR applied to 1, 1, and scalar product with nu alpha. Okay? Then, by Schwarz inequality, this is bounded by PTR1, PTR 1, 1, 1, which is 1. So this is by Schwarz inequality. Now let me call A of t this scalar product. And let's consider the derivative of A. So when I take the derivative of A, I have to take the derivative of the first term and then the derivative of the second one. When I take the derivative with respect to the first one, the derivative is given by L plus R. PT R 1 PT R1. And when I take the derivative of the second, I get exactly the same thing. So this is twice this term. Mind that in this computation, I'm never using that nu alpha is the stationary state of L. Okay? Nu alpha could be anything, any measure, any probability measure. Right? I'm not using at any point in this argument properties of this measure. It's just a probability measure. So what appeared here, it's 2 times L plus R, a function f, and a function f. So this is an operator, L plus R, applied to f, scalar f. So let me define the largest eigenvalue of this function as the supremum for all f such that f nu alpha it's equal to 1 of L plus R f f. So let me introduce this parameter, lambda, which is the supremum for all f whose L2 norm is equal to 1 of L plus R f f. Okay. Where f now it's this guy. So this, with this notation, what I have to do is I will divide that by the norm of f, divide that by norm of f, multiply by the norm square of f, and then I get that this expression is bounded by lambda. Okay? So what I proved is that A prime of t is equal to this expression. So let me divide this expression by the norm of PTR1, the norm of PTR1. This is the L2 norm, right? And then the PTR1, the L2 norm with respect to nu alpha. Right? I didn't do anything. But now this function here, if I call it g, it has norm equal to 1, L2 norm equal to 1, right? And therefore, this scalar product by this expression, it's bounded by lambda, because lambda is the supremum. So this A prime of t, it's less or equal than 2 times this lambda and then the L2 norm of 1. And this is equal to 2 times lambda, the scalar product of PRT1 with PRT1 nu alpha. And this is what I called A of T. So what I proved is that A prime of T is bounded by 2 lambda A of T. Okay? So that means that by Grunwald inequality, A of T, it's bounded by the exponential of 2 lambda of times T. But this is A of T. So what we just proved is that this is bounded by exponential 2 lambda T, and this is exponential lambda T. So I proved that this expectation, which is this expectation, it's bounded by the exponential lambda T. Well, lambda is given by this variational formula. Okay. So we just proved by using this identity that this is bounded by exponential lambda times T, where lambda it's equal to the supremum over all f with norm 1 of L plus R f times f. Okay, so this is called Feynman's cat formula. So I just proved Feynman cats. So now I'll go back. So I have this bound, and I want to apply this bound to the term. So you have to remember what we had. We had 1 over gamma n log the expectation with respect to nu alpha n of the expectation gamma n times the function. And the function is this one. So I have the gamma n, which will cancel with 1 over n. So just a gamma. And then the sum of x, fx, and v epsilon x n of eta s n square. And there is an integral. Yeah. Okay, so this is what I need to estimate. So I'll just use what we just proved. R is this function, gamma sum over x fx times this. So by Feynman-Katz formula, I know that this expectation is bounded by that exponential, and the exponential will cancel with the logarithm. So actually, by the Feynman-Katz formula, this is bounded by 1 over gamma n. Log will cancel with the t, so I have a t, and lambda. So this is bounded by this. And let's write what is. So I have t, lambda, lambda, we will write it down, gamma n. And so what is lambda? Lambda is this supremum. Supremum over all f equal to 1. And now, what do we have? We have RFF, which is RF squared. So R is this function, and this is with respect to nu alpha. So I have an integral with respect to nu alpha of this function, which is gamma summation x fx v epsilon x n of eta d nu alpha. This is an f square, of course, I forgot. Okay, so this is the term R, and R is this function times f square. And then I have plus LFF. But this is exactly what I call the Dirichlet form. Okay, remember, this is the Dirichlet form with a minus sign, because the Dirichlet form means minus LFF. So I have here minus the Dirichlet form of f. And mind that here I'm looking at the process at time n square. So this means that I'm multiplying the generator by n square. So actually I have this generator, it's the generator of the exclusion process multiplied by n square. So this will be n square, the Dirichlet form of f, and here it's the Dirichlet form. You take the generator and applied f and computed f. Okay? So this is what we get. So let's forget about t. The n will give me n here and a minus n there. And the gamma will cancel with this gamma, but I'll get 1 over gamma here. So what I need to estimate is the supremum of f2 equal to 1 of the integral of 1 over n sum fx, this function vx, let's forget about epsilon and eta, f square d nu alpha minus n divided by gamma df. Okay? And what I want to do, I want to take the limit as n goes to infinity, then as epsilon goes to 0, and finally as gamma goes to infinity. So this is what we need to estimate. Okay, let's do that. So in order to, let me compute the f, or we computed df in the last class, right? And df was the sum over all x of the rate. So the rate was 1 plus a times eta x minus e plus eta x plus 2e. F of sigma x plus e, eta minus f of eta square. Okay, so this is df. That's what we computed. Remember that this is strictly positive, so we chose a strictly larger than minus 1/2 for this rate to be strictly positive. So this rate is strictly positive, which means that this is bounded below by some constant delta times the sum of x of this term. So since this is bounded below, I have a minus sign. I can just, let me call that d0 of f. So I can bound that by minus n delta gamma d0 f. Okay? So I will work with d0, this Dirichlet form of the symmetric exclusion process. That's good. And now I need to estimate this expression in terms of the Dirichlet form. Now let us recall what is v. V is this function. So let me write this function. So let me consider this term. This term, it's 1 over n, a sum over x, f over x, and then I have v, and v, it's eta x plus e, minus this average, y minus x bounded by epsilon n, eta y squared. And of course, I have to divide by 1 over 2 epsilon n plus 1. Square f squared d nu half. Okay? Fine. So what I will do is the following. I will compare eta x with, and then eta x plus e. So I'll compare eta x plus e with its average, with minus. I will do that in 2 steps, I want to say. So first, I will compare eta x plus e with this average. And then, once I did that, I have to compare eta x times this average with this average square, which means that I have to compare what will remain. It's 1 over 2n plus 1, z minus x less than epsilon, eta z, and then eta x minus right? So, and you see that if I have a cube, I will go step by step. So first compare eta x with the average. I have one average less, and go on. So I have 2 terms to deal with. I'll show you the first one. The second one is just the same. Okay, so I'll concentrate on this one. And you see that the argument goes exactly as so I have to compare these 2 terms. So let's see. Let me write it here. It's 1 over n, sum over fx. Then I have eta x and eta x plus e minus 1 over 2 epsilon n plus 1 z minus x bounded by epsilon eta z f of eta square d nu alpha. So this is the term I need to estimate. So now I want just to say that here, well, I can, if I take z equal to x, I want to take z different from x. I have one term which is z equal to x. Eta is bounded by 1, so this term will be bounded by 1 over epsilon n. Okay? So f has norm equal, eta x is bounded by 1, so f squared has L2 norm equal to 1. So this term, this is an average, so this, if I consider just the term z equal to x, this term z equal to x, it's bounded by a constant which depends on the function f divided by n. So this one, it's a small term. So I can here assume that I have all z different from x. And I don't want z equal to x because I have eta x here. So here in this sum, I can assume that z is different from x. Right? Now let me rewrite this sum as 1 over n fx. Let me take it out from the expectation. And what I have is eta x plus e minus eta z, f of eta squared. So this is the expression I have. I will write it as 1/2 plus 1/2. And for the second term, I will perform a change of variables xi equal to sigma x plus e z. So I'm exchanging what happens at x plus e, which is here, and z. I'm taking these two sides, which are very far apart, and I'm exchanging them. Okay? Okay, maybe. Okay, maybe it's not the best thing to do, but let's do that. So I'm exchanging these two sides. So you see, what I claim is that nu alpha of xi, it's equal to nu alpha of eta. So I'm not changing the measure, because the measure of this configuration, it's equal to that configuration, because the measures depend only on the total number of particles, and I'm not adding or subtracting particles. So there will be no modification by the measure. Of course, eta, if sigma is given by that, eta is the sigma x plus e z of eta. So here I'll get f sigma x plus e z of eta, the nu alpha, square. Eta x is not moved by this. So eta x remain eta x. Sorry? Yeah, because well, alpha it's constant, right? It's a stationary state. By the point. I don't. It's here you're complaining? Ah, sure. If I'm not taking a constant profile, everything changes. But here, no. But here I'm taking the stationary profile. It's flat. Yeah. In what you're thinking, I will compare with the stationary profile. Okay, you have, well, it's not stationary, don't care. I take the flat profile. Otherwise, I'll have to take care of these terms. So you see, we started with mu n, and then I just took the entropy and then consider everything with respect to the measure which I chose. So what you'll do is you'll plug the measure you want, the flat one, for this argument to work. Okay, so here I have, change the measure, and here you see that when I exchange x plus e and z, x plus e becomes z, and z becomes x plus e. So here what I have, it's eta z minus eta x plus e. Okay, and what you see is that this term, it's minus this one. So I'll get this expression minus that one. This is what I want. Because in my Dirichlet form, I can compare f of eta with f sigma an exchange. So I want to make this exchange appear in order to be able to estimate this expression with a Dirichlet form. So when I take the sum, this is equal 1 over 2n. Then I have a sum over x, fx, 1 over 2 epsilon n plus 1, sum over z. Now let me put them together. I have eta x, let's say eta z minus eta x plus e. And now f sigma x plus e z of eta square minus f of eta square d nu alpha. Okay. So this is the difference between these two terms. Questions? Apart? Yeah, because if here I had x and I would exchange, here I would get eta x plus e. And if I get here eta x plus e, this becomes different from that, and I don't know how to put them together. And this is why I'm avoiding this special point. So now this is what I get. Now I have here b2. So I have here b squared minus a squared, which I will write as b minus a times b plus a. Okay? And that I will bound by 1 over a, 2a, b minus a squared, plus a divided by 2, b plus a squared. Right? So I have two terms, and this is true for any capital A. So I have this term. This term, what will appear, it's f plus f of sigma plus f of eta square. That I will say it's bounded by a to 2 times b squared plus a squared. I'll say that these terms are bounded by 1, absolutely bounded by 1. So I don't care of these terms. Here I will have this term and this one. This one, the integral, it's equal to 1. And this one, if I perform again a change of variable, psi equal to this, since the measure doesn't change, I'll get here phi of psi squared. Phi has L2 norm equal to 1, so it gives me 1 again. So this term is bounded by a constant times a. So this expression here, when I have here f plus f, I can bound that by a constant. because f is in the L2 norm of f is 1. Okay? So this term, I have here a contribution of epsilon n. There are epsilon n z, but this is divided by epsilon n. Here f is bounded. This gives me a contribution of n, but I'm dividing it by n. So the consequence is that this term gives me constant times a. Okay, so I'll make a very small at the end. So now we have a second term. In the second term, I have 1 over a, or 2a, 1 over 2n, then a sum. When I did this term, let's say that I put f square here, so I don't have it here. Okay, so I had f times this expression. Let me put it all here so that I don't care. 1 over 2 epsilon n z. So these are bounded by 1. And therefore, what I have is f sigma x plus e z eta minus f of eta squared in u alpha. Okay, so this is the bound I get. Constant times a plus 1 over a times this expression. And I have to bound this expression by the Dirichlet form. And here is the formula for the Dirichlet form. So you see what is the difference is that here I'm exchanging x plus e and z, which may be far apart. They are at distance epsilon n, right? While here I'm only allowed to exchange two neighbors. So I have to compare this term with that one. So how can I do that? Here I'm exchanging x plus e and z, and they are at distance, or at most epsilon n. Okay, so I took what happens at x plus e and what happens in z and exchanged. And here I'm only allowed to exchange nearest neighbor. So how you do? Well, you will construct a sequence. First exchange x plus e with x plus 2e. So you go in this way until you reach z. Then you exchange z, and then you come back. Okay? So I'll construct a sequence of configurations in which each one is the exchange of the previous one to be allowed to compare this expression with that one. So I don't want to erase the formula for the Dirichlet form. So let's see, I have here x plus e, and I have here, let's say, x plus me. Okay, so x plus me is z, so and m it's bounded by epsilon n. And what I want to do is exchange what happens at this side with what happens at this side. So let me call that x and that y. So I want to exchange x with y. So the first thing to do is to send x here. So to exchange these two. So this will be my configuration, say, eta. This will be eta 1. Then I'll send x here. And so that will be eta 2. And at eta, I guess, m minus 1, or maybe m minus 2. So m minus 2, let's say, I'm here at x. Here is x plus m, e. That is, here I have x, and here I have y. And is this the configuration eta So eta x plus 2, this is m minus 1, that's m minus 2. That's correct, okay? And m minus 2. Then I exchange these two. So this is n m minus 1 will be the configuration in which I have y and x here. And then I go back. And maybe 2m or something like that. I'll have y here and x here. So this means that I'm taking this difference. So this will be n2m, and this will be n0. So what I'm doing is that I'm writing f sigma x plus e z eta minus f of eta as f eta 2m, maybe 2m plus 1, 2m minus 1, I don't care much, minus f of eta. And I'm writing that as a telescopic sum. Okay, so this is what I'm doing. And, well, this is square. So I have a square here. Then I bound that by, well, there's nothing I can do. I'll use Schwartz. So Schwartz will give me a constant times m. Okay, so this is just my telescopic sum, and then I had to pass the square inside. And at this point, I observe that eta j plus 1, it's equal eta j, and then sigma xj plus 1. Okay? Well, sigma xj and xj plus 1, well, traveled around here. But what's important is that this, if I fix a bond here, it appears only twice. Okay? It appears once when I go in this direction, in which I exchange these two, and once when I go in the other direction, in which it appears again. Okay? So each bond here appears only twice. And at this point, when I write eta j plus 1 as sigma xj plus 1 eta j, I perform a change of variable, xi is equal to eta j. So let's write down what I'm saying. So this is the term which bothers me. And so there is 1 over 2a, 1 over 2n, so a sum of x, 2 epsilon n, don't care of d1, sum over z. And now what I did, I have a sum over j. J it's from 1 up to 2m, and 2m it's it's the size of z minus x plus m. It's z plus x g multiplied by n. Okay. So this is of order 1 over n. I'm multiplying by n to make it order 1. And now what had appeared here, it's f eta j plus 1 minus f of eta j square, d nu half. And I have an extra factor m here. So which is that? Okay, let me write it n. Okay? Questions about that? Is it clear what I'm doing? Okay? Louder?
Explain again, how do you put M in the expression?
M. So M is, I want to go from x plus e to z. So this is z. So m times e, so m divided by n, it's plus x, it's equal to z, which is that m, it's equal to z minus x multiplied by n. So m, it depends on the distance between x and z. Okay? But you just have to remind that x, it's between 0 and 1, z, it's between 0 and 1. So the number of jumps, it's x minus z times n. So this is why I have x minus z times n. But x minus z, it's bounded by epsilon. Okay? Remember that in my sum, z, here, it's z minus x, which was bounded by epsilon. So now, what I'm saying, let's change variables. Let's call that xi. And let's remind that eta j plus 1, it's sigma xj plus e of eta j. So when I perform this change of variables, since the number of particles in eta j, it's equal, so xi, it's equal to eta. The number of particles at eta j, it's the same as, because here I'm integrating with respect to eta, right? So the number of particles at eta, it's the same as eta j, because I'm just exchanging the position of particles. When I change the measure, the variable, I don't change the measure, so that will be equal to f sigma xj plus e of eta minus f of eta square d nu alpha. And I finally have an expression which can be compared to my Dirichlet form. All right? So now I have to, well, to hope that I didn't do any mistake and that everything will. So I have an, n square epsilon, and then I have a sum over all these terms, x, z, j, and m. And so here, what's appearing in this sum, it's this xj. When I sum over j, I'm summing over all the bonds between x and x plus and z. Twice, but that I don't care. Okay? This sum in j is the sum over all these bonds. So it's bounded by the sum over all the bonds between x and x plus epsilon. So I can think that here I'm summing over all bonds between x and x plus epsilon. Okay? So this is the sum. And okay, so let me be careful. This is the sum over z x epsilon. So how do I estimate this? Okay, first I will say that m, as we have seen, it's z minus x times n. Z minus x is bounded by epsilon, so m is bounded by epsilon n. So m, this m, it's bounded by epsilon n. You agree? Can I erase? Okay. So I will erase this m, and I pay here n epsilon. Fine. Now, this sum in J, it's a sum over all these terms. So Z does not appear anymore in this sum. And how many terms I have here? I have epsilon n terms. Do you agree? So I have a sum over x, then a sum over z minus x, and then a sum over all these bonds. So here, it's a sum, this sum in J, it's actually a sum over all y from x to x plus e, which are giving me all the bonds between x and x plus e, epsilon. Do you agree with that? Which means that z does not appear anymore in these sums. But how many terms do I have? I'm summing here over all z, which are at distance epsilon from x. And how many z's are there? Epsilon n, 2 epsilon n. So this sum gives me a contribution of 2 epsilon n. So 2 epsilon n, n will cancel with this n. Okay, maybe let me write everything. Right? Now I have only a sum over x, and for each x, I sum all these bonds. So for each x, I sum all bonds between x and x plus e. So if I fix a bond y and y plus e, how many times this bond will be counted? Well, in this summation, this bond will appear for all x which are at distance epsilon from y, because from this, starting from that x, this bond will appear. Because I'm summing in this second sum, I'm summing from x to x plus e. So if I fix y, the first time it will appear, it's when I take y minus epsilon. Then, because if x is equal to y minus epsilon, I'm summing over a window of size epsilon, so I will include that one. Then I will sum for y minus epsilon plus 1 plus 2 up to this bond. So how many times this bond will appear? It will appear epsilon n times. So what I'm claiming is that this sum, it's equal to the sum over all z of f sigma z plus e minus f square d nu alpha. But if I fix a bond z plus e, or a bond y plus e, it will appear in this sum epsilon n times. So this will give me epsilon n. So I get an extra factor epsilon n. And so what I proved is that the expression I started with, it's bounded by this times the Dirichlet form d0 of f. Do you agree, or is it too messy? I can start again. Tell me. So what I claim is that I just proved that this expression, it's bounded by this times d0 of f, and mind that here, so I get a constant, epsilon square, n squared divided by n divided by a. So this is my bound. And I have to estimate that by this term. So I have n times d0. So I'm fine because there I have n2. But here I have epsilon square, and epsilon is small. So that's fine, because here delta is fixed, gamma will go to infinity after epsilon, so I'm happy, because here I have epsilon square, so I can take A equal to epsilon, so it will cancel one of the epsilon, so I'll get still epsilon here, and if A is epsilon, this term will vanish with epsilon. So, convinced, or should I repeat the argument, the computation actually? Come on. Which former step? Fala em português. Tudo bem, mas eu só não sei onde você quer que eu recomece. Ali? Porque, what did I do? So what I said is that I want to exchange a particle or two occupation variables, one which is at x plus e, and the other one which is at z. So I'm calling z x plus me. And so this tells me that m it's equal to z minus x times n. And what I'm doing is that, well, I defining this sequence, so which the first term it's just exchanging x plus e with x plus 2e. So that x came here, and then I continue until I arrive here, which I exchange x to y. So x now it's at the right position, but I have to send y back, so I go back. Okay? So I define in this way a sequence from eta to the sigma x plus ez, which I'm calling n2m. Maybe it's not 2m, maybe it's 2m minus 1, 2m plus 2, but something like 2m. And so I was allowed, so in this construction, so this configuration is now called n2m. And now I write this difference as a telescopic sum. But what I'm interested is in the square, this difference square, because this is what appeared in my expression. Okay? So I first use Schwarz inequality to say that the square of this sum is bounded by the sum of the square times m. And here I know that m it's z minus x times n, but z minus x is bounded by epsilon. So m it's bounded by a constant times epsilon n. So here I have an epsilon n. And here I have this sum. Okay, this sum. So let me go back and start with this sum, which is what I wrote here. So let me erase everything. And let's go back. Okay, and so what I said is that I will just bound m by epsilon n, and I have epsilon n here, so that disappeared. So this is the expression I need. So if I have here eta j, the way in which I go from eta j to eta j plus 1 is by exchanging two neighbors. So I'm defining xj as the one which I use, the bond which I use when I'm going from eta j to eta j plus 1. Okay? So eta j, going from eta j plus 1 means that I'm exchanging xj with xj plus 1. So this defines the sequence xj. And so this is my definition of xj. So this means that I'm exchanging xj with xj plus 1 when I go from eta j to eta j plus 1. Square. Now I'm doing the following. Let me call xi equal to eta j. So I'm changing variables in this integration. But eta j, it's you take eta and then you exchange. Maybe you go back. But what you're doing, you're exchanging. So the total number of particles of eta j is the same as eta, which means that the measure of eta is the same as the measure of eta j. So when I perform this, change of variables, I'm not changing the measure, and this is xi, and therefore what I get here is f sigma xj plus 1 of xi minus f of xi squared. Okay. And now the expression I obtained, it's really close to the one d0, because I'm only exchanging neighbors. But here, what it is, in this Dirichlet form, each bond appears once and only once. Now, here it's messy. It's messy because, well, I'm summing over x, I'm summing over z, and then there is this xg. So what I have to do is to fix a bond So I take my interval 0, 1. I fix a bond y plus e. And I'm looking at sigma y plus e eta minus f of eta square d nu alpha. And I'm integrating that. And I'm asking, well, this term, when it appears in this sum, what are the x, the z, and the j's which produce y plus e? Okay, so I fix a bond, and I say, well, in this construction, which I just did, which are the x, z, and j, which turn this expression equal to sigma y plus e? And what I'm saying is that, well, what did I do? I started from x and z, and I consider everything between x and z. Okay. So which are the x which can produce? If x is very far from y plus e will not appear in this construction, right? Because in this construction, I go from x to x plus z, but the difference between x and z, it's epsilon. So do you agree that if I take, here it's y minus 2 epsilon, if I take x somewhere here, y plus e will never appear in this construction. Okay, because here, remember that I'm summing for all z minus x bounded by epsilon. So z, it's at distance epsilon from x. And here, these terms, xj plus 1, are between x and z. Okay? So my first claim is that if x is at a distance it's below y minus epsilon and after y plus 2 epsilon, there is no way that y plus e appears in this. So for all x which are outside this interval y minus 2 epsilon, y plus 2 epsilon, the exchange between y and y plus e does not appear. Do you agree with that? Okay? Or not? Or do you not agree? Tell me. Now, let's take x in this interval. Well, how many z's are in this interval? So I have to take x has to be in this interval. So how many x I have? I have between y minus 2 epsilon and y plus 2 epsilon, I have a constant epsilon n, possible x. So these are the total number of x. How many z's I have? Well, z is a distance epsilon from x. So I have, these are the positions for x. I have epsilon n positions from z. Okay? But once I fixed x and z, as I said, the interval appeared only twice. Okay? So if I have x and z, one bond will appear only twice in this exchange. So this is my claim, is that for any y, I have in this sum only epsilon n square terms which appear. So this expression will be bounded. I'm summing over all y. Well, there is this 1 over 4 an, all y. Now, I'm looking at the term sigma y plus e eta minus f of eta square, d nu alpha. And then I'm counting the number of x, z, and j, which produce y. And this we just bound by epsilon n square. And therefore, this produces me epsilon square times n. While here, I have n times a constant. So I'm happy because this is bounded by epsilon square times an times the Dirichlet form of f. So this is what I proved. And there is another term which is constant times a. I'm free to choose a. So let's choose a equal to epsilon. So that will kill one of these epsilon and add me epsilon. So I proved that the first term, it's bounded by this expression. Now, there is still minus n delta over gamma d0f. Maybe it wasn't a good idea to choose, so let me go back. Maybe it's better to, so a over there and a here. So let me choose a, which match this one. So I want to kill this term with that one. So for that, I want epsilon square, a over n. Sorry, there is n square. Here, I had epsilon square n square, so this killed and I get epsilon square n. So I want epsilon square, go back here, epsilon square n over a to be equal to n delta over gamma. So the n cancel, and this tells me that a has to be equal to epsilon square gamma divided by delta. So let me choose A like that, because if I choose A like this will kill this one, and what will remain, it's C, A, and A, it's epsilon squared gamma divided by delta, which will go to 0 when I send epsilon to 0. So we proved that the limit as n goes to infinity and delta then goes to 0, it's 0. And this is for all gamma. So the first term, which was the entropy divided by n times gamma, it's bounded by a constant for divided by gamma, and now I can send gamma to infinity to show that indeed everything is bounded goes to 0. And that completes the proof. Okay? Okay, and so this is the crucial point in the proof. So I will use this theorem next week in order to complete the proof. So we have the martingale, now we can express everything in terms of the empirical measure. It's tight, martingale goes to 0, we can repeat the same argument. Okay? So I'll go back to this proof. It's the central point. So try to do it by yourself. If you don't understand, go to the video. If you don't understand, ask me, because that's the crucial point. Or go, yeah. Okay. So we talk next week.